So let's start with our first speaker. We have Rear Admiral David Titley. Admiral David Titley served as a naval officer for 32 years and rose to the rank of Rear Admiral. Dr. Titley's career included duties as commander of the Naval Meteorology and Oceanography Command, oceanographer and navigator of the Navy, and Deputy Assistant Chief of Naval Operations for Information Dominance. He also served as Senior Military Assistant for the Director, Office of Net Assessment in the Office of the Secretary of Defense. In 2009, Dr. Titley initiated and led the U.S. Navy's Task Force on Climate Change. After retiring from the Navy, Dr. Titley served as the Deputy Undersecretary of Commerce for Operations, the Chief Operating Officer position at the National Oceanographic and Atmospheric Administration. Dr. Titley serves on several advisory boards and committees, including the National Academy of Science Board on Atmospheric Sciences and Climate and the Center for Naval Analyses Military Advisory Board. Dr. Titley is a fellow of the American Meteorological Society. In 2017, Dr. Titley was the recipient of the College of Earth and Mineral Science Wilson Award for Excellence in Service. So I will hand it over to Dr. Titley now.
Okay, well, thanks very much. Let me see if we can share the slides here and make this work. With any luck, you see my slides. Yes. And we'll go to, okay, perfect. Okay, well, thanks very much. And I will try to do this in about 20 to 25 minutes, and we'll hopefully have some time left over for questions at the end of this session. So I'm an old Navy guy, as was mentioned in the introduction. So I kind of always like to start with the bottom line up front in case we don't get through everything. Totally the opposite to how we write an academic paper, right? So here are my kind of three bullets. Climate change, whether we focus on it or whether we don't focus on it, is not going to go away on its own accord. We will either manage it or it is going to manage us. This is not free. Sometimes you hear people say the cost of energy is so cheap, it's going to be coming everywhere, there are going to be jobs, it's going to be wonderful, we probably can buy unicorns at low cost. This is going to cost us. It is certainly going to cost the military because, just as one example, preparing for sea level rise is expensive. Getting forces to be effective in the Arctic, a new ocean for the surface fleet, is expensive. This is going to cost us, and we need to be honest about that. And finally, and this is really something I've just added in the last few months, but it's been true for a long time, and this is a physics conference, right? So we sort of understand as scientists that nonlinear fluid dynamics has its own set of challenges, and rapidly growing small perturbations, start to dominate the flow regime right after a certain amount of time. Compared to the Intel folks, our stuff is easy by comparison in trying to at least understand where it's going. And we saw tragically just a few weeks ago, really a pretty big intelligence failure, right? Everybody thought Ukraine was going to collapse in 72, 48 hours, and obviously they haven't. They also thought Afghanistan was going to stay around for more than 72 hours, and they didn't. So we see that despite the tens of billions of dollars that our US intelligence community spends each year, getting the geopolitical changes is really, really tough. It's not a knock on them. People are hard, right? People are hard. All we have to deal with is physics, even if it's nonlinear and things like that. So why do I go through that? While we may not know what the future threats will or will not be 20, 30, 40 years from now, we do have a fairly good understanding of what that physical battle space is going to be, right? So we should prepare for that regardless of whether there is a specific requirement or a specific threat, because as we have seen, those threats can change in a matter of weeks and months. Our acquisition process works on a decadal time scale. So there's a time mismatch there. Okay, this is a science conference, so this should not be very very groundbreaking for anyone here. But when I'm talking to the general public, I often get questions, well, how do you guys know, and gals, how do you know that the climate is changing? Why are you so sure about that? And I like to tell people that the basics are cutting edge 19th century science. I'm sure many here recognize the three gentlemen on the lower left there, Fourier, Tyndall, and Arrhenius. We understand the equations. We understand that there are certain gases that re-radiate heat at the outgoing long wave radiation. We have a ton of observations. I'll show a couple of those slides next. And we've been able to predict it, right? We're right for the right reasons. In my field of meteorology and also oceanography, climatology, not only being right, but being right for the right reasons counts. And you can go back to Hansen's models of the late 70s and early 80s. If anything, he was conservative. He under forecast the amount of global warming. And you can look at all the various CMIP, right? The UN consortium for numerical modeling. The one I have up here, I think, ran right around the year 2000, and you can see that, now 20 plus year track record in the mean, in the average, it's really done pretty well. So we understand the theory. We have a lot of independent observations, and we can predict this. So that's why I say, we get the basics really, really well. What to do about it is a separate question. And here are just two observations. And I like these because, some last decade people were saying, oh, Noah's cooking the books and these other crazy, crazy things that we would hear. On the left is grapes. The French, God bless them, have been keeping records of the harvest in certain very specific parts of France since basically the early Middle Ages. So for 800 plus years, you can see the Julian date. So of course, the numbers on the top of that y-axis, that's later in the year, and earlier is down at the bottom there. And you can see that, of course, there's significant annual and even decadal variations, but it was kind of constant from 1400 through, let's say, 1950, and then it sort of falls off a cliff. And the same thing with the cherry blossoms in Kyoto, and this record goes back even further, roughly to 800 Common Era there. So over 1,000 years, and the same type of thing. So whether or not NOAA has correctly processed the data, not to give away the plot there, but yes, they have. But we can see grapes in France and cherry trees in Japan are all telling us the same thing. Okay. Again, for a science conference, I don't think this is anything groundbreaking, but I also get questions a lot from the public. It's like, that's only a degree. It's only 2 degrees. Why are you guys worried about this? I woke up this morning and it was 40 degrees Fahrenheit, and if I'm out west, it's 85 in the daytime. So that's and you guys are talking about 1 degree. So we know, of course, if we're with a community of scientists, we understand that 1 degree averaged over the Earth, averaged over an entire year, is a tremendous amount of additional heat. But if you're just talking to sort of the guy or gal on the street, they just kind of scratch their head about this. But sometimes this helps. This is, well, if we're in a certain place, let's say at the beginning of the graph, that was, say 50, 60 years ago, we would certainly still get extremely hot or extremely cold days. But now we get more and more of those days that really exceed thresholds, and frankly, days for which our infrastructure and our society were not really designed to handle, or certainly handle well. And we're seeing more and more of them. We still get extreme cold, as Texas can tell you from last year, but we don't get as many of those days, and we get a whole lot more on the heat. And you could do a similar type thing for precipitation, except there's actually a nonlinear function in there, so the extremes go up even faster, thanks to the Clausius-Clapeyron equation. This was the first working group. We've, of course, had 2 others come out in the last few months there, but if anybody has not had time to go through all of the 1,500 pages, here it is on one slide. And again, for anyone that's been paying attention to climate change in the last, 10, 20, 30 years, this isn't really a surprise, but we are seeing, especially on the precipitation side, and I would say it's probably with the nonlinear effects in the water vapor in the atmosphere, we are seeing some of these extremes both more and more intense than perhaps people really understood or certainly talked about even 10 or 15 years ago. If you work with the emergency management community, they have, of course, dealt with big disasters, and it's kind of what they do. That's their sine qua non, if you will. And if you go back to sort of the days of like Hurricane Andrew, or even in the 1980s, you would see that these $1 billion, and yes, this is adjusted for inflation, disasters would happen maybe once every 2 or 3 months in the United States. Now, fast forward to right now, 2020 is, I think, the last time we had the statistics for this. $1 billion disasters are happening almost every 3 weeks, maybe even a little less than every 3 weeks. So think about it if you're in charge of managing this, it's sort of all hands on deck for FEMA, for these $1 billion disasters. You had time to reset, recharge, restock. Now it's almost continuous. And we really need to take a look at, do we have both enough capacity and are we managing these in the right way? So I think there are really two related questions here on how to deal with this, because I think that those trend lines are pretty clear, and I don't see the disasters getting less frequent with time, certainly not in the foreseeable future, unless we fundamentally change how we build and how we live, and that's not happening right now. Sea level rise. Both the IPCC and then NOAA actually came out with numbers that are really pretty close to this. This is a big advance I think we have seen in the last 10 or 20 years. When it was mentioned, I was chief operating officer about a decade ago at NOAA, almost a decade ago. And back then, when I sort of really was asking some hard questions about what can NOAA say about sea level rise, the best the agency would do is they gave me a graph that showed basically 3 inches and a graph that showed me 6 feet, and they would not put a confidence interval on that. And it's like, okay, that may be scientifically correct, but it's absolutely useless if you're a coastal engineer or if you're a disaster planner. Here we have a little bit more fidelity, and we start seeing the IPCC, I think this is for the first time, really start to at least acknowledge the fact that these ice shelves, so not only the thermal expansion of the water and the glaciers, but really the big ice shelves, Greenland, Antarctica, may come down, or may turn into water, may melt in a nonlinear fashion. And that's because it's not just melting both at the top and bottom, but they actually fracture. And Richard Alley and his colleagues at Penn State have done tremendous work in this area. And I think it's starting to get acknowledged. And when you look back through the paleoclimate, you can't really explain some of the rapid increases in sea level without this function, but it's hard to model. So we now have a dashed line, and you can see where that goes. But worst case, if this particular feature takes off, we're looking at over 1.5 meters, so close to 6 feet of sea level rise by the year 2100. Now, yeah, that's kind of a worst case, but 3 to 3.5 feet, a good meter is certainly kind of likely. That's still a lot. That's a lot for a lot of people. And it's not only the physical water, it's the storm surges come in on a higher baseline. And for many places, a 3-foot sea level rise is going to have a big impact on your water table and your fresh water. And of course, once you get salt into that, you've got an issue. Okay, so let's talk a little bit here in the next 8 minutes or so on what are the climate impacts to security. And if you take a look at this graphic here, the check marks are mine, and you can certainly agree or disagree or think they're right or think they're wrong. But really on the rows, I kind of have, sort of how climate change is going to impact maritime security, military operations. So whether that's impact on the operations itself, if I was in the Pentagon right now, I would say that's change in the physical battle space, where we fight, where we train, where we fight. Impacts to bases. We generate readiness. So that's basically not only having people and stuff, but being able to execute when somebody is pushing back. We have seen a tremendous example of not being ready, as portrayed by the Russian army here in the last month. And you can see it's really catastrophic. So you want to be ready. We generate our readiness at our US bases and our training ranges. The humanitarian assistance and disaster relief, it is a mission the United States Department of Defense, along with many of our partner militaries. Frankly, we do this very well, but how many times are we going to keep on doing this, and how much more does that increase? And at some point, if you're doing that, you're not training for the higher end fight. And then amplified security threats. Sometimes I say climate change doesn't make things bad, but they make things worse. They make bad things worse. So how does climate change, where is that going to happen? And I'll show some examples. And then the rows here really are, do we need more of what we do today? Does it impact that readiness, or is it actually potentially new missions? And I'll try to give a couple examples here. So here's just an example of changing the battle space. Usually I talk about the Arctic. It's kind of the poster child. The Navy doesn't really have surface ships that work very well up in the Arctic. But I was on a committee. I was working with retired Colonel Mary McRae. She did her doctorate at Villanova. And we were talking when she was looking for things to do, and she wanted to do something useful for climate change and security. Let's really take a look at how the changing climate may impact aircraft performance. So it's at the margins, kind of the bottom line for her dissertation. It's at the margins, but often in our planning, in the US military's planning, we are planning on nearly full aircraft working on very short landing strips, maybe in the summer in a high heat regime. And if that heat gets more and the humidity gets more, both of which reduce aircraft performance, then the plans that we have today may not work. So there's, do you have more aircraft? Does it take more time? Do you need longer runways? Do you need more powerful aircraft, better engines, or whatever? These are things that, again, it's not that we can't figure out a solution, but we don't want to be surprised by it. Here's just, and you can read the slides faster than I can, but just some things for the Navy to work on. Weapons and sensors, acoustic atlases. So of course, not only is the atmosphere changing, but the ocean is changing. And how those vertical density gradients change really drives how you find submarines. So our climatology, our average, what we really put together in the 70s and 60s and 80s, how has that changed? And has it changed so much we need to redo those atlases? The bases, this is a picture from a few years ago of Offutt Air Force Base. So I'm not going to show you the storm surge coming into the Gulf Coast here, but this is in the middle of the country. 2 to 3 billion with a B dollars worth of damage to our base where we host the U.S. Strategic Command. $3 billion worth of damage, even in the Pentagon. That's like real money. And you have to go, on your knees to Congress and beg for more money because we self-insure, which really means we go to Congress and ask them for more money. And at some point, they're going to get tired of writing these continual checks. And of course, that's money that's not doing something else. The humanitarian assistance, I've kind of mentioned that. The picture on that center right there, it's an aircraft putting flame retardant on fires. We are burning through hours in our Air National Guard. And there's, it's a great thing. They're obviously helping, saving lives and property out west. It's a tremendous mission. But the issue is if you're doing that, and then we have a contingency in the DOD, the Department of Defense, calls up, let's say, California or Utah or Wyoming Air National Guard to go do something overseas, they may have gone through their hours. They may be out of crew. They're basically out of Schlitz, for those of you who remember that. And that becomes an issue. So this is the capacity issue. And then finally, here's my links between weather and climate response. And you can see why I'm a meteorologist and not a graphic artist here. But unfortunately, it's not this nice one-to-one thing. Really bad climate means really bad society response. Sometimes you can have a really bad climate impact in an extreme event and very little or no society response. That event either didn't meet a threshold, and an example of a threshold is when Sandy went into New York. The storm surge got just above the lip of the subway stations, and all you need is just above with the Atlantic Ocean, and you fill up the subway. Had the storm surge been about a foot lower, we would not have flooded out the subway. So that's a good example of a threshold. And then how does society respond? If you're Syria and Assad, you actually make things worse. If you're many other countries, you try to mitigate the suffering, and you may not then get a really bad disaster response. So just a couple slides to close here. Some things to think about. The migration, I think, is going to be a huge issue. We saw migration out of Syria. That was 1 million people, and it nearly brought the European Union to its knees. You can see these numbers, they're pretty big, and how this works is going to be an issue. Domestic pressures, as we have towns and cities in the US that are sort of repeatedly hammered by extreme events, what does that do to our own society? Geoengineering or climate intervention is being studied, and it's quite controversial, but it is one way to change the climate. Certainly, if you can bring greenhouse gases, primarily carbon dioxide, out of the atmosphere, put them safely back in the ground, that's lower risk to the climate, but it's expensive. The other way is by, let's say, putting things into the atmosphere, like sulfites, like almost simulating a very long-lived volcano, relatively cheap, but really unknown consequences. I was on one of these committees for the Academy, and basically my tagline for the solar radiation management or albedo modification is it doesn't make the climate go backwards, it goes sideways. So do we jump out of one problem and find ourselves in a worse? A lot of issues with that. The administration's interested, so we're seeing therefore the Department of Defense is interested again. The Undersecretary of Defense for Policy, I understand, is going to shortly announce an Assistant Secretary of Defense for Climate Change and Energy. Lots of bureaucratic motion. You can see they put out a lot of good documents, and I've read them since I have no life, and they're actually very good. The challenge is going to be, of course, with the execution. I just showed this sometimes. This is probably a graph many people have seen. It comes courtesy of AAAS, and it's inflation-adjusted non-defense research. And what you can see in both general science and energy is, although we've talked a lot about the climate issues, when you look at the money, we haven't really changed our money. So it's hard to convince me personally that we're particularly serious about this issue. I had a brief from Maersk shipping company, the big shipping company. They're actually doing things. Believe it or not, they are actually going to be running net zero, no kidding, net zero ships, not just paying money to somebody and calling it net zero, but really zero carbon ships. They've built one, they're testing it with real cargo, paying cargo, and they have a plan to get themselves by 2030 to be to about 50% reduction, and by 2040 to be, no kidding, net zero. So it may not be the governments that lead the way here, and industry, I think, we hear a lot about sometimes industry is not helpful. I think in some places industry can be very helpful. So how's our government going to help? We either are going to, we're going to have the energy transition, but we're either going to retard it or we're going to accelerate it. And that's really what the government policy is going to do. Well, let me stop there. And I think we've left enough time for questions, and I'll be happy to turn this back to the moderator. Thank you very much.
Thank you, Dr. Titley.